Hello fellow students, today we are going to talk about double slits. So let's just have a question to start with. In a double slit interference experiment, the distance between the slit is 0.5 millimeters. The yellow light of a sodium lamp is used with a wavelength of 589 nanometers. And the question asks us to calculate the angular separation between the first and the second broad fringes on the screen. And these are 4 marks. So how are you going to do this question? If you got a question that has a lot of marks and you don't know how to start, one of the good thing to do is draw a diagram. So let's draw a diagram first. It's a double slit experiment. So we will first draw 2 slits here. So I have drawn 2 slits here. And then you shine light through these 2 slits. So I use the red color here, but it's actually yellow light. But anyway, this light here, you pass through these slits and diffract through these 2 apertures and then interfere on the way. And then finally, when it reaches the distance screen here, you show a diffraction pattern. So a diffraction pattern is basically bright and dark fringes. I will draw like out here. So this one is a central maximum. So this rough sketch of the diffraction patterns, this is the central maxima, which has an order of m equals 0. And this one is the first order maximum, and this one is the second order maximum. And then the question asks us to calculate the angular separation between the first and the second bright fringes. So it's basically this thing and this thing. The angular separation is basically if you draw a line here and another line here, the angular separation is basically this angle. So how I'm going to calculate this angle here? First thing, you are going to record that we have a formula here. The double slit equation says that d sine of theta m is equal to m lambda. So this theta m here is defined as if you draw a line through the horizontal here, and then this theta m here, this one will be the m theta for the first order maximum, and this is angular displacement from the central maximum of the second order maximum. So you can see that if you want to find this angle, what you're going to do is you're going to calculate this angle out first and then subtract this angle, and then you can have this angle. So now we know what to do. We'll just proceed to the math. I will erase all this. So if you're going to find the smaller one, the angular displacement of the first order maximum, you are going to just substitute m equals to 1 here. And the same thing as well for the m equals to 2 here. You just substitute it in here and you get the angular displacement of the respective maximums. And then you just solve for the angles, because we are going to take their difference later. To solve is very easy because I have a lambda here and a d here. You just basically divide this d over to this side, and then you take the inverse sign here, so you can get this. And then you do the same thing for the second angle. And then for the angular separation, you basically just take the difference of these two. So it's this one minus this one. And then you're basically done because you have all the things you need. This lambda is the wavelength given you here, and the d is the separation between the slits, also given you here. So now you just substituting all the values in. The only thing you need to be aware of is the units here. This lambda here is given in nanometers, so you need to multiply a factor of 10 to the power of negative 9 here to get the value in meters. And the slit width is given in millimeters, so you need this 10 to the power of negative 3 factor here to also get the quantity in meters. So these 2 meters can cancel out, and it giving you no units inside of the inverse sign. So after you just punch these all numbers in your calculator, you can get this full result. And this result is basically an irrational number, and you need to round it to 3 significant figures because the question's parameters given is also 3 significant figures. And you are done. That's what I'm going to do for this question. The 4 marks basically comes from this initial formula is just 1 mark, and then you solve for each respective angles. This another mark, and then you substitute the value in with the units conversion. This is the 3rd mark, And then the final answer with the 3 sign figures. This is the 4th mark. Now we are finished with the practice question. We are going to generalize our results now. We are going to find a simpler formula for the question. So in the last question, we noticed that the angular separation between the 2nd order and the 1st order maximum is giving us this formula. And more generally, you can show that because the sine of the angle of the nth maximum is basically proportional to the maximum itself, the number of maximum. And then another maximum, the nth one, you just replace n with n. And then we can do similar things as in our last question. We just solve for these 2 angles separately. You divide this d over and take the inverse sine. And then if we take the difference, we can get the angular separation of basically any 2 maximums. So this will just be the difference between their inverse sines. But however, this formula is very cumbersome. In the last question, if you try to enter all these things into a calculator, you will find that it's a very long expression because it's composed of 2 inverse sine terms. It would be nice if we could have this formula here. So it tells us the angular difference here is just the sine of it is just proportional to the difference between the number of maximums. So what we done here is we basically just replace this and this with their difference version. And if this relationship is true, the angular separation will just simply be you divide this d over to the other side and take the inverse sine. And you see now it's just a 1 sine term. It's much easier than the last one. And we can actually test it out. If this formula that we kind of showed in last slide is true, then we can actually do the first question a lot simpler, like this. So we just substituting all the values in. Because it's the angle between the 2nd and the 1st order maximum, their difference is basically 1. So you actually don't need to do anything here. And this one is the wavelength, and this slit separation. And after you punch this simpler equation into a calculator, you will get this. The last several digits is a bit different, but if you round it to 3 sign figures, it's basically the same answer. And because the numerical values of the 2 answers are basically the same, this gives us a strong hint that this approximation may be true. But as you know, just because 2 things have similar values in their numerical answers does not mean that they are the same. It might not be true. We want to actually prove that this relation is actually true, at least approximately equal. And seeing this relationship is true is equivalent to say this is true, because we just divide this d over here, which is the sine of the difference between the angles is approximately equal to the difference between the order of maximus times the wavelength divided by the slit width. So how am I going to prove this relationship? Well, first thing we're going to do is we're going to use the sum and difference identity. That says the sum or difference of 2 angles in a sine, you can expand it like this, which is the product of sine and cosines. You may remember this formula from your 11th spec math. And for our case, we just replace this x here with our theta m, and the y here is theta n, and we take the minus sign. And then we just basically do the same thing on the right hand side. And then we are going to use some physics now, the double slit equation, which I have seen several times now. So we can basically replace this sine of theta m here with m lambda over d. So we just divide this d over to the right hand side. And the same thing as well we can do for sine of theta n. We can replace it with n lambda divided by d. And now the next thing for the cosines, we use the Pythagorean identity that states that the square sum of the sine and cosine is equal to 1. So to get the cosine, we just basically move this sine to the other side and take the square root. So it will be like this. And then we can use our double slit equation again to replace this sine, these 2 sine here with their respective n lambda or m lambda divided by d. So this is the relationship, the equation we have worked out in the last slide. Next thing we're going to do is use the binomial approximation. So this basically tells that 1 plus x to the power of a is approximately equal to 1 plus ax, given that x is very small. This formula is very useful in all sorts of places because it can basically simplify your expressions and tells you how your equation basically looks like, at least in the limit as x is close to 0. And in our case, this a here is basically this square root thing, which you can also write it as a half power. And the x is basically this thing, and lambda over d and the square and minus sign, or is this thing. And this approximation is valid because in the typical double slit setup, the wavelength of the light used will be much smaller than the slit separation. So the wavelength of light, visible light, will typically be in the range of 10 to the power of -7 meters. And the slit width is basically like 0.1 or 0.5 millimeters as in our last question. So it's in the magnitude of 10 to the power of -4 meters. So if you divide these two things, it will be like 1 over 1,000th. So it's very small. And it will become even smaller after squaring. It's like 1 over a million. So it's very small. You can safely use this approximation. And now you just apply the formula, which just bring a half in front of these square terms, and also this term. Now you just expand the bracket. You times this to this and times this gives you these two terms. And the second two terms, you do the same thing as well. Then you basically group light terms together. I group this and these two terms together. So lambda over d is common expression. We can take it out. And this left us with m minus n. And this first term, you can see is already looks like something we like. And for the next two terms, we just expand it. There has an n squared, which is this, and the m here. And this is a lambda over d squared, and there's another one here, which gives us a cubed term. And the second term, we just basically do the same thing. And now, what I've done in this step is I take it out m times n in both of the terms. And in the first term, there's a negative n, and in the second term, there's a positive n. So I can group it together. So I can group them together, which gives us m minus n times m times n, and then a cubed term here. And then we have this expression here from our last slide, approximate equal to, beware, because we use the binomial approximation. And the next thing we are going to notice that, as said before, the quotient of the wavelength over the slit width is very small, which would become very, very, very small after cubing it. So you can try to calculate what's the cube of 1 over 1,000. And thus the second term is basically 0. So you can basically ignore this term. The half is just some constant. It doesn't do much in these scales. And the m and n in a typical double slit setup, you won't observe maximums or minimums past 20 or 10. So their product won't be very big, and this is extremely small. So you can basically drop this second term. And if you drop the second term, it gives us this, which is the sine of the difference between the angle of maximums is approximately equal to the difference between the order of maximums times the wavelength divided by the slit width, which is exactly what we are trying to prove. So we can write a black square here, which means the end of proof. So we just prove a useful relation, but actually that's not the end of the story. We can actually have more approximations and even simpler formula for us to use. So recall that the Taylor expression or Maclaurin series of sine is this. So you can write sine x as x minus 1/6 of x cubed plus some other terms. This is for x very small and measured in radians. So this one is a very useful relationship or formula to use. You should definitely remember it. It's very useful. Another thing to note that is x must be measured in radians, because this formula basically comes from a calculus, and in calculus we always use radians. So if you remember, the derivative sine is cosine, and that only works if x is in radians. But now let's get on to physics stuff. use the formula we just proved. So we have just proved this part of formula, and then we can rewrite the sign as this. So I basically just substitute x with theta m minus theta n, and you have these terms here. And now, if m and n is close, such as being consecutive integers, their angular difference will be very small. So if you have seen your teacher do a double slit demonstration for you, or if you have do a double slit experiment yourself, you may have observed that the angular separation of basically the bright dots on the wall is very, very small. That means we can just ignore the cubic and higher power terms. Because as I said before, if you have a small thing, you take that to the power of 3 or to the power of 5 or 7, it will be even smaller. And it's basically nothing compared to the first term. So we can just ignore the higher power terms and keep only the linear term. And this will give us this relation. As you can see, we just basically only get rid of the sign here and left out what's left is only the number inside the bracket. This is sometimes called the small angle approximation, which you may have seen when your teacher derived the double slit formulas for you. And now, angular separation is basically this right hand side here, and this is equal or approximately equal to the left hand side. So this formula tells you that the angular separation is approximately equal to the separation between the numerical value of the maxima times the width length divided by d. And now this formula is very, very simple because there's not even inverse sign here, just some bunch of numbers timed together. But remember that angular separation delta theta here will be measured in radians because we have used this formula. And now we can have a test of our formula just derived. So our formula just tells us the angular separation will be this, and using the value from our first question is the second order maximum minus the first order maximum and times the width length divided by the slit width, and this gives us this number of radians. But in a typical physics question, you need to give your answer in degrees. So how do you change from radians to degrees? It's very simple. You need to remember one key fact, that pi radian is equal to 180 degrees. So this is a very important conversion factor. You may have seen it in your year 11's math method. So how I'm going to do it is you basically just times this thing, your answer to this conversion factor. In converting, you either use 180 over pi or pi over 180, depending on which way you are going to convert your unit. But your goal is you need to cancel this radian with this radian. These two units need to cancel, and this thing is basically equal to 1 because these two things are equal, and you are multiply by 1 here, you don't do anything. You cancel the radian, you multiply the number, and then you are left with the degree. And as before, the last digits of the answer is slightly different, but if you round it to 3 single figures, the numerical value is literally the same as before. So this tells us that our approximation is a reasonably good one. And that's all for today. Thank you guys.